All right, a couple things I want to touch on that I don't know if I hit too well yesterday. One of them being the calculus videos. So again, trying to give you the resources available to be successful in calculus. Dr. Richard Delaware in the math department a few years ago had gone into the studio and recorded himself basically lecturing to a videotape, just like he would in the classroom. And so he has many, many hours of lectures for calculus, up to Calc 1. So at the very end of Calc 1, everything's going to be covered. And he begins with a really good overview of college algebra and trig. So if you need that little extra help or you want to see something, an example I showed the last class would be maybe, let's see, not necessarily graphing, maybe inverse functions. So a function inverse to another function. When do inverse functions in their graph exist? And then inverse trig functions. So maybe we wanted to talk about inverse trig functions. For some reason, Blackboard doesn't like to open tabs that's going to take you outside of Blackboard. To get away with that, if you just open in a new tab, it goes straight there. If you just click on
Although the most familiar...
Sorry, if you just click on it, a lot of times it'll give you an error depending on what browser you're using. So if you open a new tab, kind of saves you from that. When he did these videos, he would just go and he did it on VHS, and then eventually they put it on YouTube, but they put the whole tape on YouTube. So it's like 2 hours or 1 hour chunk of lecture. So we've broken it down into the topics that he covers. So these links will take you to that section of the lecture where he starts talking about it. And then it will just continue on. So it doesn't ever necessarily cut you off, but you can kind of see you go until you hit the next section, and then you can stop.
Familiar sorts of inverse functions we will be looking at will be the exponential and logarithmic functions.
They're pretty good quality. It's nice because you don't have to necessarily write everything down, but he does. So if you're taking notes with them,
you're guaranteed of an inverse.
That's good.
So that's what we will do.
You can skip ahead.
And what I
so okay,
equal to 1 over sine x. So
maybe
you've just
I don't understand
simplified
what he's doing
this
here.
complicated.
So you can watch that and see how that works out. And we will talk about this triangle today in inverse trig. I mean, basically, it's pre-calculus smashed together in a few lectures. So, I mean, you can take a whole semester of pre-calculus and actually learn this stuff, but we're assuming coming into calculus that you've seen it before, so it's just a refresher. So we don't hit it as hard. But it will come up when we do the calculus part, and I'll be expecting you to know how to deal with that. So there's Dr. Delaware's videos. All of them are links here, relatively easy to use. So eventually when we get to the very end, chapter 6, there's also videos for that. I posted yesterday's lecture on online lectures. I also posted the notes on class notes. Did I go over the theorems from the book with you guys? I don't know if I hit. Okay. So the last thing I want to talk about with Blackboard is a lot of you didn't buy a book, which is perfectly fine, but I wanted you to have some hard copy of the theorems because I'm not going to write out the theorems like I did last semester. Talking to some students, they felt it was kind of a waste of time to write out the theorem. So I'm going to copy, screenshot the theorems from the book and then paste them all in a Word document. And about halfway through it, I have chapter 1 posted, and I'll probably have the rest of the chapters we talk about posted by the end of this week. But I'm not going to write out these theorems, but I might write in my notes, okay, let's look at theorem 1.1. Then I'll pull this up on the board. Now, all this is being recorded, so if you go and watch the lecture, it's going to flow pretty smoothly, but I'm not going to necessarily take the time to write this down. So you're not going to have the time to write it down in your notes. If you want to leave a paragraph or leave an empty spot in your notes to write in the theorem, that's fine. But I'm going to try to save some time in class and do more examples and more Wiley problems than just hit you with these theorems. So we'll talk about the theorems, and then we'll do an example about how these theorems work. So I will pull this up more than likely. If you print it out, there's only like maybe 7 pages a chapter with the theorems if you print them front to back. It's not going to take up that much space. If you have a 3-ring binder, just put them in your notebook and then pull them out. Then you can look at them, write on top of them, do whatever you need to do with them. So I only have chapter 1, but I'll have eventually all 6 chapters that we will talk about on their theorems. All right. Are you ready for calculus? Any questions on the Are you ready for calculus sheet? Question? Okay. So we'll abbreviate, are you ready for calculus? Probably makes no sense, but I don't want to write it all out. So number 1D, we have 9 minus x to the minus 2 over 3 plus x to the minus 1. Sorry about that, guys. Okay, multiple ways you can look at this. You could factor it right now. You have a difference of squares on top. You could rearrange it if you just like dealing with fractions. Difference of squares is probably going to be the fastest attempt. So let's kind of, this would be 3 minus x to the minus 1, 3 plus x to the minus 1, over 3 plus x to the minus 1. So the 3 plus x to the minus 1s are going to cancel. Here, you could write this as 9x squared minus 1 over x squared over 3x plus 1 over x, right? Because I found a common denominator to be x squared, so I have 9x squared minus 1 over x squared. Does that make sense? I might have skipped an extra step of writing 1 over x squared here, but hopefully you can make that leap with me. So then here, I have 9x squared minus 1 over x squared. If I flip and multiply, have that cancel. Here, 9x squared minus 1 is a difference of squares, right? It would be 3x plus 1, 3x minus 1. Go ahead and write that. 3x plus 1, 3x minus 1 over 3x plus 1. This is going to look, okay. So you see that? I also have an x in the denominator from this x. So the 3x plus 1 cancels and 3x plus 1 canceled, and I'm left with 3x minus 1 over x, which would be 3 minus x to the minus 1. Which up here, if I canceled these two, would be 3 minus x to the minus 1, which would be the same answer. So more than one approach. This one's a little cleaner, but this one gets you there. Question?
Sorry, can we like factorize if the sign, the ratio sign is different? Because the 9 would be like 3 raised to the power 2.
3 to the power 2, yeah. So it's a
Can we still factor it like that when the x is 3x raised to the power minus 2?
You would have to have the square root of 3 squared. You could. So the question was, can I factor 3 minus x to the minus 2? I can't do 3 plus x to the minus 2 because that's not a difference of squares.
Like 3 to the power of 2.
3 squared?
Yeah.
So then I would have, like if it was this?
Yeah.
Well, that's exactly what that is. It's just not written in that form.
Yeah, but what I'm saying is that because the x is having minus 2.
That's fine. So here, anything in the form a squared plus b squared. So here the b, what is b? It's 1 over x. Yeah, so it is squared. It's just, does that make sense? I could rewrite this 3 squared minus x to the minus 1 squared. So my b is x to the minus 1. So then it would end up being 3 minus x to the minus 1 times 3 plus x to the minus 1. That minus 1 is playing the role of b, if I do a squared plus b squared. Sorry, a squared minus b squared. You cannot factor the sum of squares. Any questions on that? Yes?
On the second example, how did you get from the 3x minus 1 and then the bottom x right below your fingers?
This x?
No, down. So, and then to the right answer, where did
So I split up my denominator. I have 3x over x minus 1 over x.
Okay.
So anytime if you have a plus b over c, you can write that as a over c plus b over c. But do not wait, let me see. Please don't a plus c plus d. Write this. That is not correct. Do not put, you cannot split the denominator, you can only split the numerator.
So will you explain how you did it with the 3x thing? So you did 3x over x and then the minus 1x over x, and then the minus 1x over x does the x to the negative power, and then the x disappears on the 3.
Yeah, they cancel.
Okay.
Yeah. Good. So one comment I want to make, eventually I will post the answers to this, and it's just going to be the answers. So probably by 5 o'clock today, I should have these completed and posted on Blackboard under that answers. Number 4C, you're asked to you're asked to solve the area for a cone, no, not a cone, a cylinder, for R greater than 0. So you want to rewrite this and then this becomes a quadratic, right? This is a quadratic in terms of R. So this is a quadratic in terms of R. So then we have this becomes, I'm going to use lowercase a. This becomes b, and this becomes c. And then we use r equals negative b plus or minus the square root of b squared minus 4ac all over 2a, being one way to solve for that. And then you're going to take the positive one because it wants the radius to be positive. So then you just simplify those terms. You're going to have a 4. When you take b squared, you get 4 pi squared h squared. So you have a 4 in both these terms, so you can factor it out the square root to be 2. You'll have a 2 here, so you can factor out the 2 to cancel the 2's and simplify it that way. So does that make sense? Sometimes it just has to be exposure to these types of things to think of them. So if you haven't been exposed to something like this, it might make it difficult to solve for it. Question?
I think I did it right. I was just wondering 3e.
3e. 3e, the answer is b times a to the minus 3 over 2. Yeah. Any other question? Any questions on the trig? You guys try to do the trig part? I know it's kind of towards the end, which I don't know how much time you had to work on it. So I will give the quiz over this material at the end of class tomorrow. So we can also, you can answer any questions after I post the answers. Question?
Yeah, on number 12, part 2, finding the range of
Mm-hmm. Yeah. So we have number 12, and we have the function g of x equals 5x minus 3 over 2x plus 1. So the domain we talked about yesterday being all real numbers except x cannot equal minus 1/2, right? How you write it is pretty open. You can write it minus infinity to minus 1/2 union, minus 1/2 to positive infinity. You could write all real numbers except x cannot equal minus 2. You can write it out. But the question was on the domain?
the range.
The range, sorry. What would be the range of this function? Think of horizontal asymptotes, right? Because that would be outputs, right? So if I talked about graphing this in college algebra, we would find we have a vertical asymptote at x equals minus 1/2. How did we find horizontal asymptotes?
It's the top over the top coefficient over the bottom coefficient.
If and only if
The top one is greater.
the powers
I
are
mean,
equal.
If the degrees are equal.
Yeah. So so if you recall, we'll say horizontal asymptotes, if I have a function, let's just call it h of x, if that's ax to the m plus something over bx to the n plus something, the horizontal asymptote is y equals a if m equals n, is y equals 0, I think, if n is less than m. No, wait, let me think for a minute, sorry. Yeah. M is less than n, so yeah, which
bottom is greater than or equal to 0.
Y equals none if n is greater than n. So if n is greater, there's not. So if we look at so we can think of an example. Y equals x squared, right? It has a larger, and I don't have any horizontal asymptote. I could say cubed if you really want to look at one that has no horizontal asymptote, right? No horizontal asymptote. And the numerator is greater than the denominator. Y equals 1 over x looks like this, and it has a horizontal asymptote at y equals 0. If they're equal, the horizontal asymptote is at a over b. So here the horizontal asymptote would be 5 over 2, right? So the range would be all real numbers except x cannot equal 5 over 2. Question?
Where you wrote the y equals none, and then the y equals 0, y equals none, the same thing. They both say that it is greater than n.
Oh, sorry. I wrote that. So m needs to be greater than n. Ugh. The denominator needs to be greater here, so I need to flip this to m and this to n. Yeah. Thank you. Question?
How did you figure 5 over 2 then?
5 over 2?
Yeah.
It's because that's a horizontal asymptote. It can never equal that. It just always approaches that.
Why wouldn't it be 5
Did I write it down incorrectly? No. So
Oh, okay. I was looking, it says y equals a.
it should be a over b.
Okay.
Thank you. Yeah, you guys got to catch my sloppiness. So, yeah. So it should be a over b. Thank you. Make sense? Coming back somewhat? Any other questions?
Did you ever want on number 5, just any of them? Maybe just seeing the y.
Completing the square?
Yeah.
So pick one for me.
A.
A. So let's look at number 5A. Number 5A, let's see here. So number 5A, we have y equals x squared plus 4x plus 3. So let's complete the square, because I think that's going to help. So I have a x squared plus bx plus c. And I need to complete the square. So I'll have y equals that. Sure. Y equals that. So completing the square here, I get c to the other side because this is the part where I'm completing the square. It makes it more interesting when a is not 1. So that's why I wanted to do a general example. Like on b and c, a won't be 1, so we'll go through this. Yeah, we'll do b then. So let's go through just the general recall how to complete the square. So I have y minus c equals a x squared plus bx. I want my coefficient to my square term to be 1, so I'm going to factor out that a and make my life a little easier. So I have y minus c equals a times the quantity x squared plus b over a x. So now I need to add something to both sides to have a perfect square. And if I add it to this side, I have to add it to that side. I have to be a little careful because when I add it in the parentheses, I'm really adding a times that. So I need to add a times that to the left-hand side. So does anyone remember what I need to add to complete the square?
A over B, or yeah, B over A squared.
Close. It's B over. Okay.
Is it a squared?
It's the B over 2A.
Okay.
But A here's 1. And B is B over 2.
Okay.
So it's 1/2 the B term if A is 1.
Right.
But if A is 1, you need to factor that out, make it 1, and then your B term's B over A. So you always add B over 2A squared, right? So I'm adding B over 2A squared, but really that means I'm adding B squared over 2A, right? So this would be Y minus C plus B squared over 4A, right? Because it's the whole thing squared. So I had an A squared, but this A canceled it when I added it on that side. Does that make sense? Eventually, if you go through all the way through this, you're going to derive the quadratic formula. So you have, so if y is 0, the quadratic formula, right? You said a quadratic equation equal to 0 and solve the quadratic formula, y would be 0 there. Okay, so we're on this side. Since I completed the square here, I have a perfect square. My perfect square is x plus b over 2a squared. Now, if b is negative, it would be x minus that, right? Because whatever's under the parentheses is what you put here, plus or minus, depending, squared. So this gets you to a point where you can just rearrange the equation. I think they like it in the form where you have a large, let's see if I can show you here. This is the form they want you in. So I have that squared, and then I have b minus a number. This is just a number, right? So I'd add that together. The c, b squared. So let's look at b, since b is a little bit harder than a. We'll look at b. We have this 3x squared plus 3x plus 2y equals 0. So we're asked to complete the square, so we're going to complete the square on the x's, because that's what's squared. Move the y to the other side. So I'm going to pull out the 3. I'm left with x squared plus x plus something equals minus 2y. Now, whatever I put here, I also have to put here. I have to remember that I have a 3 in front, too, so I have to deal with that. So completing the square here, what I'm going to add, right, b over 2a squared. b is 1, so I have a half squared. So I'm going to add 1/2 squared, so I'm really adding a fourth. I'm adding a fourth times 3, so I added 3/4 on this side, so I have to add 3/4 on this side. Is everyone happy with that? Some of you are looking at me like, ooh. Very good question. I'm adding a fourth here, right, on this side in the parentheses because I want this in parentheses to be a perfect square. But I have this 3 out front to deal with. I didn't want to deal with it at a, but I have to deal with it when I add a fourth to this side. I'm really adding 3/4 if I distribute my 3. So I have to add 3/4 on the other side. Question?
So where was the A in the completed part?
The a here is 1.
So you take out the 3 to make the A 1.
Correct.
So then it's always going to be the 2 on the bottom square, which is b to 4.
Yes. So this is, b is 1.
But then you got to think about distributing it, and then you put on the other side.
Yes. So now, at this point, I made this to be a perfect square, so I still have my 3, and then I have x plus 1/2 squared. Because if I have x plus 1/2 squared, I get what's in parentheses here. So I designed this number to be perfect, so it's a perfect square. Which is kind of nice in math. We can do that. Then on this side, I have minus 2y plus 3/4. And I believe that is the form they wanted in. So they could potentially want, I guess, the coefficient on y to be 1. So dealing with that is pretty straightforward. Divide both sides by minus 2. So your answer here would be minus 3/2 x plus 1/2 squared equals y minus 3/8. And this would be the form they wanted in. The coefficient on y is 1, plus some constant, they call it b, or minus some constant, and then some constant times x minus a constant or plus a constant squared. Any questions on that? Completing the squared? Completing the squared does come up in differentiation and integration when we go to do it. Dealing with this problem, I don't really know what's going on, but when I get it to this form, all of a sudden I know, oh, well, this is a quadratic that shifted to the left 1/2. It has a horizontal component of minus 1/3, so then it shifted down and squeezed in a third, and then it shifted up 3/8. So that's the whole point of completing the squares, so you can visualize what's going on with this function. I couldn't begin to graph 3x squared plus 3x plus 2y equals 0. I could solve for y, then I'd have some quadratic. If I complete the square, this gives me, oh, it's shifted to the minus 1/3, you know, things like that. It's shifted down. So now all of a sudden, I don't have a minimum, I have a maximum. Does that make sense? Because quadratic, you would have a minimum of the function, but since it's being multiplied by this negative number, it's going to be a maximum. Which will be a big part in Chapter 4 when we talk about maximizing and minimizing functions. You probably did that in college algebra, but you only ever did it with a quadratic, because there's only one critical point on a quadratic, and that's the vertex, which will show up on that Are You Ready for Calculus? Find the minimum of that quadratic, which is the vertex. All right, any other questions?
So in C, when you take the y over, all the terms are in y except for one x constant?
Yes. So you're going to do the exact same thing, except you're going to complete the square with y. Okay. I've posted the Wiley assignments. So if you go to your instructor's view now, or not instructor's view, your view, your section 2 of calculus, and I've posted 4 assignments. Only 2 of them are due Monday, and the other 2 will be due the next Monday. So review, we've talked about some of the review problems, pretty straightforward. Find the domain and range of functions. There's some log functions in here. Find the inverse formula. Do you guys remember how to find the inverse formula? You take y equals x, switch the role of x and y, and solve for y, and then you have an inverse function. Properties of logs we talked about a little bit last time. I didn't lecture over it, but test you to see if you know that. So this is going to be due Monday at 11 p.m. Everything will be due Monday at 11 p.m. unless I extend it, and it's possible that I would have to extend it. All right, so we're going to move on to 1.1. 1.1 is kind of a short section, which is nice, and it's an intuitive approach, so there's not a lot of calculus to it. We're going to look at graphs of functions and determine if a limit exists. So we have this new concept of a limit, but we have more of an intuitive approach to what it means versus what it means algebraically. So back to here. So this is 1.1. Limits and intuitive approach. There's 2 parts of calculus. There's differential calculus and integral calculus. Your book in Chapter 1 kind of introduces this as like a storytelling type part, but the first probably 10 weeks of the semester, we'll focus on the differential calculus. Differential calculus, so, is all about answering the question, given any function, so we'll call this function f of x, we're going to answer the question, what is the slope of the tangent line through one point? Differential calculus. So we want to know what's the slope of the tangent line at one point. College algebra, you guys did this multiple times with 2 points, right? Find the slope in between 2 points. Find the equation of the line given 2 points. But now we'll be looking for the tangent line. So this is the tangent line. And there's multiple applications of this, and we'll do some of them later on. But if this was a position over time curve, if I said, okay, I went to, this is how much time it took me to go to St. Louis and, Columbia and all those different places, if I have a function that represents that, I can find my velocity at any given point in time, which is kind of a new concept to think, how fast are you going at one instant in time versus your average velocity, because for velocity we mean distance over time, right? So it's like I traveled this far in this amount of time I have my velocity. But now using calculus we can say at this moment in time I'm going X miles per hour. Various different applications to this. So this is differential calculus. There's also integral calculus. This will be chapter 5, chapter 6. And that will answer the question, given a function, f of x, finding the area between 2 points. So this is finding the area underneath the curve. So we'll spend majority of the time on differential calculus, but we will get into integral calculus. And integral calculus can be beneficial to find total distance traveled. If I integrate a position over time curve, I can find the total distance I traveled from time equals 1 to time equals 5. A lot of the applications are more physics engineering based, but there are some in biology and chemistry. If you integrate a reaction curve, you could say potentially how much of the substance A is being used, how much of the substance B is being used, if it's making a new substance, at what rate is that increasing, at what rate is A decreasing, how much total substance was made in a given point of time. This is also used in the medical field with drug delivery, how much your bloodstream can absorb, how much drugs in the bloodstream at any given point in time, and how much the body can absorb and how much can it get rid of. So there's balances to that, how much doses you want to take and the time the time it takes to do that. So there's a lot of applications. A lot of times we don't get into the applications because they're ugly. If you take more specific courses, you're going to use the calculus we do here to apply it in those cases. But it's kind of getting the baseline. I try to spin it to be like, this is something you do in an engineering course or biology course and stuff, but sometimes it makes the problems really ugly. So we'll just say, this is a random problem. Don't ask where it comes from, because it doesn't really exist in the real world, but we're going to work on it. Okay, so that's kind of the introduction to calculus, per se. So let's look at 1.1 in more detail. So let's look at theorems. From 1.1, and of course this is on Blackboard. So if you want to print that off, and you'll actually have the copy. But I'm going to pull it up. Okay, so the first theorem we have on 1.1 is this informal view of the limit. And this is just more linguistics than actually calculus. So this symbol means the limit as x is approaching a of a function equals L. So they can kind of tell you how to write it. It means the function is approaching L as x is approaching a. So you have to keep in mind that if I just draw a graph of a function, say 1.1.1, I'll make it relatively straightforward. Let's say this value is L and this value is A. So my x values and my y values. My x values are my input to the function and the y values are the output. So as here I take the limit as x approaches a of my function equals L. There's also, you can see here, if I get closer and closer to a, my output gets closer and closer to L. If I get closer and closer to a on this side, my output gets closer and closer to L. You guys see that? So the limit as x approaches a of the function goes to L. So the next theorem your books talk about is one-sided and two-sided limits. So 1.1.2, this symbol is saying the limit as x approaches a on the right. The limit as x approaches a on the left. They don't have to be the same. If you think of this example right here, this 1 over x, if I approach 0 from the left, I'm going to minus infinity. If I'm approaching 0 from the right, I'm going to positive infinity. The limit on the right or the left always exists. But if the limit on the right and left do not equal each other, then the limit doesn't exist at that point. So you have general limits, left side limits, and right side limits. Right side or left side limits are always going to exist. You're going to look at the function, you're going to travel along until you hit 2. The left side of 2, you'll look at the left side of 2, so all numbers less than 2. And then you'll look on the right side of 2, all numbers greater than 2, but getting closer and closer to 2. If they go to the same point, the limit exists at 2. If it doesn't, the limit doesn't exist at 2, but the limit on the right and the limit on the left will always exist. So that's the last theorem that talks about it. The limit at the point A will exist if and only if the right side limit and the left side limit equals L, equals the same thing. If it doesn't, you write does not exist. So let's look at some examples. Let's just pull up the book 1.1 and look at examples from the exercise. Okay. That's a good one here. Oops. So the answers, okay. So this is a crazy graph. This is example number 8 in your book. The first question is find the limit as x approaches minus 2 from the left of the function. So this is the function. Oh. So this is the function. It's crazy. I'm looking, the inputs are getting closer and closer to 2. What is the output getting closer and closer to? To 1, right? So I'm getting closer and closer to 2. My output's getting closer and closer to 1. What about as x approaches minus 2 from the right? So I'm on this side of 2. I'm getting closer and closer to minus 2. So if I asked you, what was the limit as x approaches minus 2? What would you say? Does not exist. The limit does not exist there because the limit on the right doesn't equal the limit on the left. That's that last 1.1.3 theorem, saying the right side limit has to equal the left side limit for the limit to exist at the point. Okay, what's the left side limit at 0? 0. What's the right side limit at 0? Minus infinity, good. What's the left side limit at 4? It's kind of crazy. I can't really tell. Let me see if I can zoom in. Oops. It looks like it's not getting smaller. So could I, what was that, 4E? Okay, so I kind of lied to you. There's only one instant that a left side limit or right side limit wouldn't exist, and that's in an oscillation case, where it's just going back and forth and it's never going to go towards something. If you look at sine and cosine, if I talk about the limit as x going to infinity, that's always oscillating, right? This one is just bouncing back and forth, so it's not a continuous function, but it's not getting closer to anything. An oscillation that would look like, you know, something like this that's dying down, so this would go to 0. But it's not damping, which doesn't exist in the real world because we have friction. So if you talk about physics, you're always going to have damping unless you're in a vacuum. So if I have some kind of oscillation motion, if you talk like a pendulum, okay, so it's not really getting closer and closer. In a vacuum, it would never stop. But since we have damping due to friction in the air, because there's friction in the air, it's going to slow down and eventually go to 0. So we haven't invented anything perpetual motion that's going to be constant. So this doesn't really come up in the real world. But if you do have something that looks like this, the right side limit doesn't exist. So it's a very, very unique case. But pretty much anything I give you, anything you see on an exam or final, is right side limit's going to exist to be something. Here, the limit as x approaches 4 on the right goes off to infinity. So most of these problems in this section, this would be the example of oscillation. However, the limit exists on everything that's given. What is the limit as x goes to 0 from the left? 0. What about on the right? 0. What is the limit at 0? 0. What's the value of the function at 0? 0. So just because it's an oscillation, don't get caught up on the limit's not going to exist. If I talk about the limit at infinity, that would be it doesn't exist because it's going to oscillate back and forth. So let's look at the Wiley problems from this section. So the Wiley problems from this section. The first graph, pretty straightforward. It looks crazy, but you're doing the same thing. The limit as x approaches -2. Both being positive infinity, right? If it's a general limit, you have to look at both sides. But if it's a one-side limit, you only have to look at one side. So the example, the limit at x equals 2 is not going to exist. But the left side of 2 goes to 1, the right side 2 goes to -infinity. So the right side limits exist, but the limit at 2 doesn't exist. The graph of the function, pretty straightforward. I'll just kind of show you. You can put your points on here, and then if you put your graph, you can't modify this graph except move it. So if you need a function that's going to be in this domain, then you need to put these points on here because you notice that they're open circled here. Does that make sense? A lot of times some students will try to move this or try to flip it or do something crazy. You can't do the graph. A lot of the hard work is done for you. You just have to place it in so it satisfies these conditions. So given the graph, can you verify the limit? Given the limits, can you match that to a graph? So you should be able to work both ways there. So here the value of the function at -1, 0, and 1 need to be 1. So that kind of gives you these 3 dots. And then the limit as x approaches -1 from the right needs to be 4. So that means that this open circle dot comes up here to -1, 4. After that, you really don't have any choices. You just want to verify that the limit as x approaches 0 goes to 4, which it clearly does, and the limit as x approaches 1 from the left goes to 4, which it does. So then once you have that, submit the answer. And I was off my points. So it says my graph, my points, so let's repeat with new values. Get this correct here. Points. The value of the function at -1, 0, and 1 is 0. The function is defined. The limit is, and this, now it changed to 1. So I need to pull this down here to be, so if I approach -1 from the right, I go to 1, 1, 1. If you zoom in, you can see kind of where your points are. That's my answer. Okay, that's correct. So I think maybe one of my dots were actually off. But it's pretty straightforward. This is the last one I want to do, so we have, I think, enough time to do this one. So find the equation of the tangent line to the graph of y equals x squared at a point. We don't really know how to do that yet because we only know how to find the slope between 2 points, right? So what if I found the slope between 2 points and those 2 points being the same point using college algebra? So let's look at an example from Wiley. I'm going to do this one in class, and then there's the very similar one with x to the 4th, and I'll let you guys do that on your own. So example from Wiley, we have y equals x squared. What was the point? negative 4, 16. Perfect. And then the point is negative 4, 16. And I want the tangent line at minus 4, 16. This is the question. So if I graph this, I have this point minus 4, 16. Right? So what's a general point on this quadratic? If I plug in 1, I get 1. If I plug in minus 1, I get 1. If I plug minus 2, I get minus 4. What would be a general point? If I plug in x, what am I going to get?
X squared.
X squared. So I'm going to call a point, a general point on here, x comma x squared. So now I have 2 points, and I can find the slope between 2 points, because I know that from college algebra. But I really want the slope at the point x equals 4, y equals 16. So if I can simplify it, because now if I use negative 4, comma 16, and negative 4, comma 16, I get 0 as my slope, 0 over 0, which gives me issues. So I'm going to have my slope is y2 minus y1 over x2 minus x1. So in this case, I'm going to call my red point the second point and my point given my first point. So if I do that, the y component of my red point would be x squared minus 16 over x minus minus 4. So now if I plug in x equals minus 4, I have 0 over 0, which doesn't give me the slope. So I need to simplify this. You guys see how I could factor the numerator? X minus 4x plus 4. And the denominator is x plus 4, which is great, because that's going to cancel, and then I can evaluate this at x equals minus 4, because I can find the slope at the point x equals minus 4. So what is the slope going to be? I plug it in this equation. And if I plug in x equals minus 4 to this equation, I get negative 8. So the slope equals minus 8. I have a slope and I have a point. So I use the equation for the line, the point slope equation for the line. So I have y minus 16 equals minus 8 times x minus minus 4. And then I solve for y. So y becomes minus 8. I have minus 32, but plus 16, so I have a minus 16. X minus 16. So this is the equation of the tangent line to this original point. So this is what it would look like. Right? We didn't use calculus here. We used college algebra, right? Question?
How do we get the line x equals negative 4?
Okay, so I want to know what's the slope at this point, x equals minus 4, comma 16. This line means evaluate this equation at minus 4, if that makes sense.
Yeah.
And that's something we'll use a lot when we get to integration. So whatever I have here, I'm going to evaluate it at x equals minus 4. When I plug in minus 4 to this equation, I get the minus 8. So if the next problem that you do, your equation is going to be y equals x to the 4th, and you might have a point, a lot of times it's 2, 81. And then when you plug that in, you have x to the 4th minus 81. So you have a difference of squares twice. And then you always should be able to cancel your denominator. If you're not able to cancel your denominator, you did not factor your numerator correctly. Or you're missing a negative or something. So the slope here, you can kind of evaluate it from the graph. It should be negative. If you got a positive slope and you're on the side, you know you probably did something wrong. What do you think the slope would be at 4, comma 16?
Positive 8.
Positive 8, right?
So how did you know where to draw the line?
This line? So a tangent line touches a curve at exactly 1 point. I mean, it's not an official line. That's the second time I've done that. It's not an official line here. I just know that this is a rough estimate of what a tangent line looks like. It would look like that. So sometimes if you can connect it graphically, you can convince yourself, okay, -8 seems reasonable. Where if you're over here and you get a negative slope, you're like, wait a minute, I probably messed up somewhere because it doesn't even look like it would be negative. Make sense? All right, so this is all for 1.1. Try to do the homework over 1.1 on Wiley. If you have any questions, let me know. Tomorrow's the quiz. The quiz will be given at the end of class. I will post the answers to the Are You Ready for Calculus this afternoon, probably by 5 o'clock, 5:30. If you have any questions, bring them to class tomorrow. We'll review, go 1.2, and take the quiz.